All right.
All right, so I still have a few more minutes before I'm going to start, but before I do, everyone here is comfortable with Moose, I hope. I don't actually show it a whole lot, but it's in there. And actually, I don't even do that. I use MooseXDeclare, and so if anyone's not comfortable with that, do you need a quick explanation? Okay. So Moose, you know Moose? Yes? Okay. It still makes you write some amount of boilerplate, like use Moose, and, well, I guess you have to use MooseXDeclare, so that's not a big deal. But you have to package and use namespace autoclean, and at the end, package, arrow, meta, arrow, make immutable, and some other good stuff like that. Plus, if you want method signatures, you have to load those, and whatever. So MooseXDeclare uses the magic of devel declare, which is almost like source filters, but not nearly as dangerous, and does a lot of that stuff for you. The syntax is pretty readable, as long as you're not like, whoa, what's that? It's MooseXDeclare. And if you want to learn more about it, there's goodish documentation, and I'm happy to talk about it too. But one further thing is there's a method signatures modifiers, which lets you use method signatures as MooseXDeclare's default method thing. So I do that too.
And you have used it without incident.
I've used it without incident.
Okay.
Actually, the reason I use it is because if you use it incorrectly, either of them, the method signatures ones gives you much better failure messages. The stuff you get out of the default method handler gives you a lot of stuff, which eventually you can use, but it's a lot of stuff to read. I'm getting a little closer, so I'll put in one of my other little notes. I have this talk on GitHub, including all the source of all this stuff to use to make it. All code you'll see in my talk runs. I'm going to show you all of the code that I use for my examples. I will not show you all the code I use for my full simulation because you just really don't want to. But that's on GitHub too, and you can go look at that. So, cool. Wait just another minute or so.
Do you want to get your crazy virtual machine idea going?
No, I didn't. I didn't. I had overreached. And honestly,
That's good.
If I had started with using the Staccato sandbox that's online, I probably could have had it done. The fact that I was trying to host the Staccato at my work computer turned out to be something that essentially I can't do. Not because you can't do it, but because I need to have another IP address for the guest, and I only have one. I have one, so I thought I had it. Right. You know, like, oh, look, I can run this VM and I'll be able to. But the way you configure it because of MDNS and stuff I don't understand, I didn't quite get there. And then, of course, I wasted all my time trying to set that up, so I didn't get the other thing running, which I probably could have done if I'd gone right to there. Anyway.
What is your GitHub?
Oh, I'm sorry. My GitHub is Berger. Yeah, the talks are YAPC 2012, and then the thing just under that.
YAPC PNA.
Probably YAPC NA 2012. I don't know. I did that. I have little hope to go to any of the further ones. I would love to. I don't know that I can afford them. All right, so I guess I'm ready to go. I am Joel Berger. I'm a physics PhD student at the University of Illinois at Chicago. I'm going to talk to you about the work that I'm doing towards my thesis. You don't really need to know that it is, but it happens to be. Quickly, talk about differential equations. I'm giving you sort of a strange definition because it goes towards what I need to do. Let's say you have some number, some variable, and you know how that variable changes with time. Well, it turns out if you take that, multiply it by a little slice of time, you can figure out where it is now after that little slice of time. And you can keep doing that and eventually build up a picture of how this object moved or did whatever it does. In principle, this can be a function of lots of complex things, but for now, you don't have to think about that. So a real differential equation will look like something like this, where M is the money in your bank account, and R is your interest rate. And here you see that the rate of increase of your bank account is related to your interest rate and the amount of money you have in it. So the more money you have, the faster it grows. You know this. You've heard of the exponential growth of, a continuous compounding of interest. That's what this is. And when you solve that equation, you just get your principal times the exponent of the rate constant you have and the time. Oh, well, that was all I meant. So that's a differential equation. And you can do that on pencil and paper. That's about a 4-line differential equation. It's pretty easy to do. Sadly, most aren't that easy. So you use numerical methods to solve them. So this is my machine. It's the top half of an electron microscope. We're prototyping it, so it doesn't look anything like that. The things we're interested in right now are we have a photocathode, and the whole point of this is it's going to be a pulsed one driven by a laser. So we have this piece of metal here that when you hit it with the laser creates electrons, pulsed because it's a pulsed laser. We have some magnetic lenses, which for our purposes here basically act like optical lenses do for light, except these do it for electrons. And I have a detector back here. The detector doesn't really mean anything, it just means where we're going to look at the pulse. So the laser comes in, we generate some electrons. The electrons go through the optics and hit the detector. Of course, this looks like it's a continuous beam. That's because it's hard to draw this pulsed. But the width of the beam follows that path, and of course it makes little slices along the way. Now the length of the pulse, it turns out there are actually optics that behave like lenses for the length. This thing here is an RF cavity, and just trust me, because I don't have time, I would love to talk about it. It, as it goes through, causes the beam to contract as it goes forward, rather than expand. Again, all of this would be not too hard if these were light, if this were photons, but they're not. They're electrons and they repel each other. They repel each other more the closer they are to each other. So as you're doing all this, they're trying harder and harder to get away from each other. And our research is centered around how can we control this? How can we set these systems up so that we get them just to where we need them before they do something bad, but while they're still good? So we need to model this. We need to write software that will do this. So a little simplified picture. And what I really need is I need to compute this width and length of the pulse as a function of time as it goes through that column. And note that the generation, which, from the photocathode, which I didn't show here, and these optical elements all add terms to differential equations. I have 7 differential equations that are governing this, and there are terms that get added on, sometimes multiple from different objects, and it becomes very confusing very quickly. And so you don't want to do this by hand. You don't even want to set the problem up by hand. So I really wanted, this is a very new field, and there's really no software for it. So I kind of wanted something that I could give to colleagues, give to collaborators, and say, use this. It's easy. Well, that means I have even an extra layer of complexity. How do I make this easy for my users, not just for me? A quick look at sort of the state of the art. No one's doing exactly this, but there are things that did beam tracking. They don't have, so what I say is they don't have 6D means like I don't have the longitudinal 3-space momentum computations and whatever like that. Don't worry about that. It just doesn't do everything I need. And these are, of course, back for 20 years ago. These are hosted at national labs. They're for slow computers by our standards. So they made them really, really optimized for speed. Well, we don't really need that anymore. In fact, my little laptop does better than some of these computers that they were doing back then. So they're not usable. They were really tuned for that. They're really hard to customize. They're near impossible to comprehend. And honest to God, this is the message that, if you go to that website, is right there when you use it. Don't attempt to change anything. Find an example that's close and tweak it until you get it right. That's not what I want. I want something usable. I tried to write it in Mathematica. I actually succeeded to some amount in that it ran, which shocked the bejesus out of the people who wrote some of this stuff. And it does do pretty printing of the math, so that's one pro. But it's closed source, it's expensive. It doesn't have objects, so I can't make this API like I'm imagining it. It doesn't even have key value pairs. It makes passing stuff really hard. And the whole thing was rather slow because it does part of the simulation symbolically, which I wish I could tell it not to, but it does. There's a cool language that many of you probably haven't heard of called Modelica. It's really cool. It's object-oriented, and the attributes you give to the objects can be differential equations. It will compose them, build up a differential equation system, and solve it. But it's a little more static than I wanted. It lacks a has-a property, so I can't pass electron objects to lens objects, which I guess I could have gotten around with big if statements, but I didn't want to. And the composing the differential equations is not 100% trivial. So before I get to my actual code, let's talk about when you do a solver, you not only care about where it is now, but you have to remember, of course, where it was, because you're going to plot the whole history of this thing. So I made a little trivial example of a moose roll, which is, I should look at it on this screen because it just shows up over there, called Remember History. And when you assign to this, it actually has an array in the background which will keep all the old values so I can pull it out later. Just makes it easy. It's kind of sugar. That lets me use this object as both my where am I and all the history, so I don't have to keep track of two data structures to do that. Really, this only works with fixed width solvers, which I'm going to show you as an example here, but of course those are slow if you really want to do real work. And I'd be happy to talk to you about how I got around these problems, but I don't have time. So the adaptive solvers can't use these. So again, this is all real code. And so I got a couple slides here that have code, but ignore most of it. Listen to me. First of all, I'm using MooseX declare, as I warned some people, and my remember history role and the method signatures way to do this. But all you really have to see is I have force objects. They have a strength and an effect. The effect is a code ref. I also have thing objects. They have mass, position, and velocity in one dimension. And those have remember history trait, so they'll remember themselves. Onto the solver class. Again, don't look at most of it. Just see it has a start time, an end time, a step width, what the current time is, and it has an array ref of things and forces, and some initialization. Of course, the time also has remember history role, so it'll remember the times too. The evolution is pretty easy. We take a thing. This is method signatures. We take a thing, we get what its current velocity is, and this is really the only fun step. We take out all of the forces from our simulation object, we pull out their effects, and we have sort of a callback structure, which you'll see later how I use it. But believe me, this just takes what the effect is on the object right now. And we map them, and we sum them, and we get a force. So we can then get the acceleration, force over mass. And then we just assign to thing Vx old velocity plus acceleration times dt. And we do the same thing for the position, except we didn't have to store it first. I forget why I did that. Oh, because I want to use it here, but I want to use the old velocity. Right. So we've evolved now our position and our velocity. And then I actually have a run method which does that repeatedly until we get to the end of the time that I care about. That's all the code you need to do a fixed width differential equation solver. It's not very pretty, but it works. And this would be your user-facing script. So you're a user, you wanted to use this. All you need to do is make a thing with a mass, a force. I'm calling this the accelerating force. And it's just a strength 2. And I'm just saying that force is always on. There's always, in the whole world, there is this force with an upwards direction of 2. But I have this downward force, and it's really strong. And the closure that I give it is return 0 if it's below 0.1. But if it's above 0.1, it's got 30 down. And so now we composite these together, just in an end time of 5. It assumes a start time of 0. Things, forces, run. And I use PDL to plot it. And I get that. Actually, I'm going to do better. I'm going to get that big. Oh, but I have to make that. There it is. And so look, it goes up, and suddenly it's in the region of influence of that force, and it gets whacked downwards. But, of course, that force no longer exists, so it comes back up, and whack! But it's now up there longer, so it gets whacked down harder. And it's a cool simulation. And it would be probably fairly difficult to write these things in some other language. But it was actually pretty easy if I just call code references equations. So that was fun. How much time do I have? Am I almost, oh gosh. Quick. All right. One other little thing I want to mention. It's not really important, but unit handling. My side of the script works in a certain set of units, but my user might not do that. And of course, the great example is the Mars Surveyor. And I asked Larry earlier, and he claims he wasn't a part of this, but I'm going to still say, sorry, Larry, NASA screwed up. So their software did force in newtons. A user entered a force in foot-pounds, and we lost a $1 billion observer off into space, we think. It may have burned up in the atmosphere, but we think it went out. We don't even know where it went. Isn't that cool? One guy entered a thing in foot-pounds, and we... Anyway, what that means is there's this implied covenant between your programmers and your users to always use the same units. Use the same units. But that's probably undocumented, and it's always action at a distance, and it's unexpected. But we have Perl and we have Moose, and we want to do this better. So I wrote this, and this is really cool. And as unlike the other one, which these both are on CPAN, I recommend you look at this if you might want to do this. We make a string to number coercions, which have anonymous unit types that are related to the unit you want to do your calculations in. So this is just a num, and it will behave like a num as far as your code cares. So you're not working with number objects of some weird variety. These are numbers. The coercions are the cool thing, and I just show that the meters per second works. You can use units like you'd expect. It uses physics unit underneath, which I've been working with the developer to help improve a little bit, but it was pretty good in the first place. So here I make my spherical cow, and it should have been in units meters. And if he would just put radius equals 1, it would have assumed meters. But he put radius equals 1 foot. And when I go to use that down here, it says, you know what, that's not the right thing. I need it to be a number. But I've got this cool coercion in there, and when it converts from a string to a number, it actually converts the unit as well. And I get out 0.3048. So they gave me what they have, and I give them back I use what I need. Of course, it doesn't do the other way back, so they have to know that it's coming back out in my units. But we'll assume that's okay for now. I don't know how to do that the other way. So now that we have all this, and I've gone really through a lot of material very quickly, I hope you're not too lost. Let's go back to my example. I have on CPAN, and this is the one I'm most proud of, Perl GSL differential equation, diffeq. This uses code refs, but it uses the GSL differential equation solver by tricking it into evaluating Perl code refs at every time you call it. So it has all the power of the Perl of the GSL's differential equation solvers, like RK8 solvers. These are really fast and really smart. They can do all kinds of error numerical error estimation and things like that. But you can do it from Perl. And I have other Perl GSL wrappers in that same namespace, and you're welcome to contribute to it. It's fun. So what does this look like? And so this is my user-facing script. Can you all read it? Good enough. I've only used the type coercions because it's been me so far when I'm doing EVs. Of course, I need joules inside, so even I wanted to use EVs in the front. So I have my EV string right here, but that's not the important point. The important point is all I'm making are objects. I have this really complicated thing, but I have a laser object, an accelerator object, and then their arguments are, of course, just physical quantities about them: width, length, voltage, some solver ops. We get down here. This one is actually the main simulation object, the physics UEM column. This is on GitHub under physics UEM column. You can run it, and this example is in there too. It doesn't have any tests or anything or documentation, so that's why it's not on CPAN yet, but it's going there eventually. I make 2 lenses. I make an RF cavity. Each of them needs to be pushed into the column element. The column element is like a holder for all the different column elements. And look at this. Sim propagate. That's the whole thing. Your user calls that one time. I wrap it in a PDL call so I actually get PDL out so I can graph it. I'm using David Mertens's beautiful new Prima-based plotting engine. Beautiful in its internals. It's a little rough on its look, but forgive it that. It's really cool. And remember, Mathematica could barely do it and did it in 2 minutes. The thing I had done before took about an hour. This is called a Cook triplet, by the way, this system, so that's why it's called Cook. Everything that happens before it tells you what iteration number it is moosex declare boot time. Poof.
Wow.
And there it is. And you can see, here's your first, the red line is the width, the green line is the length. Here is your first lens. Here it hits the RF cavity. Here it hits the second lens. They both come down, because I've already tuned it, of course, down to a focus. Presumably that's where my detector is. And you're done. And your user didn't have to think about anything. He made objects, he pushed them into simulations, and it runs. And I think it's pretty cool. To my knowledge, it's the first time this has ever been demonstrated, so you're on the leading edge of science. And beyond just this is not just about my talk. This is a paradigm. You can use this. You can use this in your own codes. It won't look exactly like mine, but you can think like it. Think of equations as code references. And the rest kind of just follows from there. And you can look at this to kind of see what I did. You can talk to me. I'm happy to talk about it. I'm really excited about it. But basically, as long as I thank the people who pay me, I'm done.
They're watching.
They are watching. So thank you very much. I'll be happy to take a couple questions. I do have one more talk, like right after this, but this is the one I'm more excited about. So,
in physics and probably engineering and so on, Python is like the language
it is.
People use. So do you get grief for writing?
I do.
And so,
But I tell you what, and I was thinking about this last night because I was kind of expecting this question. And of course, you probably could do something similar to this in Python. I did it in Perl because it's what I know. But as far as I understand, Python 2 at least doesn't have full closures. They have lambdas. And the differential equations I'm building actually are compositions of closures. So I have closures inside of closures all pointing to different things to build up the equation like I want it to. And I'm sure you can do that with lambdas, but I kind of feel like I wouldn't want to. So I could be wrong. I'm not a Python guy. But the flexibility of Perl let me do this very easily and without having to think about it too much. But good question.
We did similar things with Simulink.
Is that Modelica based? I think that might be.
It's on MATLAB, and it's a graphical environment, so you do everything to do the objects and the differential, the solvers to do it graphically, and you put it together with blocks. And
I think underneath it uses Modelica. I might be wrong, but I'm pretty sure I saw that.
No, Simulink is a MATLAB thing. It's a MATLAB.
No, it is. But no, Modelica is a language spec, not a language. And I think that Simulink, okay, he's shaking his head, but.
I mean, Simulink's very old.
Okay, I could be wrong. I could absolutely be wrong.
From my experience, people need much longer to create the model. It looks nice because it's easy to
graphical.
To explain something. It's easy to catch errors, but it's impossible to maintain. You don't see dips. If someone changes it, you have to log into it. It's much bigger.
It's expensive.
It's expensive.
There's a good one.
It is real time. Okay. So you can use it in real systems to check something if your laser works.
I'm actually hoping to work with David. David's got a Prima REPL, which I think this is now running fast enough that I could probably figure out some way to put a slider bar or something for like the focal length of the second lens and do that. I haven't done it yet. We were hoping to before this talk. Didn't get there. But yes, it's cool to. I'm happy there are other ways to do it. I hadn't found them.
I prefer your way much. It's much easier to maintain, and I think it's fast enough. If not just optimize it.
Right. Thank you. Anyone else? I'd probably take maybe one more.
If you look at
I could probably take two more. Huh?
Look at Sage.
Again, it's just Python. So I have looked at it, and I'm happy that someone is trying to make something that will compete with Mathematica.
Right.
I'm absolutely happy about that. I don't use Python, so I don't know it very well. But I'm actually very happy they're doing that. Anyone else? If not, please come see me later. If you have any questions and you didn't want to ask, I'm more than happy to talk about this. Thank you all.